Article 725 addresses the requirements for remote control circuits, signaling circuits, and power-limited circuits. Specifically, when dealing with motor controllers rated over 600 volts, Article 725 mandates a minimum conductor size of 14 AWG for the control cable used for remote operation. This requirement is in place to ensure the mechanical strength and current carrying capacity of the conductors are sufficient for the intended application, minimizing the risk of conductor breakage or overheating. Article 240.4 pertains to the protection of conductors against overcurrent. This section generally requires that conductors be protected by overcurrent devices, such as fuses or circuit breakers, sized according to the ampacity of the conductor. However, Article 240.4 also provides exceptions, allowing for the use of smaller conductors than would typically be permitted if the equipment or installation is specifically listed for such use. This exception is crucial in understanding the interplay between Article 725 and Article 240.4 in the context of remote control circuits. The key point is that the exception in Article 240.4 is conditional. It applies only when the equipment or installation is explicitly listed or designed for use with conductors smaller than those normally required by the conductor's ampacity. In situations where the equipment is not listed or designed for smaller conductors, the general rules of Article 240.4 prevail, and the conductor must be protected at its rated ampacity. For the scenario with the medium voltage switchgear and the electrically operated breaker controlled from a remote location, the breaker control voltage is 125 volts direct current. The control bus within the breaker is protected by 15 amps fuses. The question revolves around whether 16 AWG control cable can be used for picking up the remote start/stop commands, considering the requirements of Article 725 and the exception in Article 240.4a. Given that Article 725 requires a minimum of 14 AWG control cable for remote control of motor controllers rated over 600 volts, the initial inclination might be to adhere strictly to this requirement. However, Article 240.4 introduces the possibility of using smaller conductors if the equipment is specifically listed for such use. In this specific case, the breaker control bus is not listed for use with conductors smaller than 14 AWG. This means that the exception in Article 240.4 does not apply. Since the breaker control bus is not listed for use with smaller conductors, the general rule of Article 725 prevails. Therefore, a 16 AWG control cable cannot be used for picking up the remote start/stop commands. A minimum of 14 AWG control cable must be used to comply with the NEC requirements. Let's delve deeper into the considerations for selecting the appropriate control cable size. Firstly, the ampacity of the conductor must be sufficient to carry the expected current without overheating. The ampacity is the maximum amount of electrical current a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides tables that list the ampacity of various conductor sizes and types, taking into account factors such as insulation type, ambient temperature, and the number of conductors in a racewire cable. Secondly, the mechanical strength of the conductor must be adequate to withstand the physical stresses of installation and operation. Smaller gauge conductors, such as 16 AWG, are more susceptible to breakage or damage than larger gauge conductors, such as 14 AWG. In industrial environments where control cables may be subject to vibration, abrasion, or other mechanical stresses, it is essential to use conductors with sufficient mechanical strength to ensure reliable operation. Thirdly, the voltage drop in the control circuit must be within acceptable limits. Voltage drop occurs when electrical current flows through a conductor, resulting in a reduction in voltage at the load end of the circuit. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The amount of voltage drop depends on several factors, including the length of the conductor, the current flowing through it, and the conductor's resistance. Larger gauge conductors have lower resistance and therefore result in less voltage drop than smaller gauge conductors. In remote control circuits, where the control voltage may be relatively lower, it is important to minimize voltage drop to ensure that the control signals are reliably transmitted. Article 725 provides requirements for Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. These classifications are based on the voltage and current levels of the circuits, as well as the power limitations. Class 1 circuits are those that operate at higher voltage and current levels and are not subject to the same power limitations as Class 2 and Class 3 circuits. Class 2 and Class 3 circuits are designed to be inherently safe and are subject to more stringent power limitations. The specific requirements for conductor size, overcurrent protection, and wiring methods vary depending on the class of the circuit. In the case of the medium voltage switchgear, the control circuit is likely to be a Class 1 circuit, given the 125 volts direct current control voltage and the 15 amps fuse protection. For Class 1 circuits, Article 725 generally requires that the conductors be sized in accordance with Article 310, which provides ampacity tables for various conductor sizes and types. However, as discussed earlier, Article 725 also mandates a minimum conductor size of 14 AWG for remote control of motor controllers rated over 600 volts, regardless of the ampacity requirements in Article 310. The purpose of this requirement is to ensure the mechanical strength and reliability of the control cables in these applications. The overcurrent protection requirements for Class 1 circuits are also specified in Article 725. Generally, the overcurrent protection device must be sized to protect the conductor in accordance with its ampacity. However, there are exceptions for specific types of circuits, such as control circuits for fire alarm systems, where the overcurrent protection may be sized differently to ensure the reliability of the system. In the case of the medium voltage switchgear, the control bus is protected by 15 amps fuses. This means that the conductors in the control circuit must have an ampacity of at least 15 amps to be properly protected by the fuses. A 14 AWG conductor typically has an ampacity of 15 amps or greater, depending on the insulation type and installation conditions. Therefore, using a 14 AWG conductor would generally meet the overcurrent protection requirements. However, if the control circuit were to be modified or upgraded in the future, it would be important to re-evaluate the overcurrent protection requirements to ensure that the conductors are adequately protected. In summary, the interpretation of the NEC requirements is correct. A 16 AWG control cable cannot be used for picking up the remote start/stop commands for the medium voltage switchgear. A minimum of 14 AWG control cable must be used to comply with the requirements of Article 725, which mandates a minimum conductor size of 14 AWG for remote control of motor controllers rated to over 600 volts. While Article 240.4 allows for the use of smaller conductors in some cases, this exception does not apply because the breaker control bus is not listed for use with conductors smaller than 14 AWG. Therefore, the general rule of Article 725 prevails, and a 14 AWG control cable must be used. In addition to complying with the NEC requirements, it is also important to consider other factors, such as the ampacity of the conductor, the mechanical strength, and the voltage drop in the circuit to ensure reliable and safe operation of the control system. When selecting control cables for industrial applications, it is advisable to consult with a qualified electrical engineer or contractor to ensure that the cables meet all applicable requirements and are suitable for the intended use. They can provide guidance on conductor size, insulation type, shielding, and other factors that can affect the performance and reliability of the control system. Furthermore, it is essential to follow the manufacturer's recommendations for installation and termination of control cables. Proper installation practices can help to prevent damage to the cables and ensure that the connections are secure and reliable. Improperly installed or terminated control cables can lead to a variety of problems, including shorts, opens, and ground faults, which can disrupt the operation of the control system and create safety hazards. Regular inspection and maintenance of control cables are also important to ensure their continued reliability. Control cables should be visually inspected for signs of damage, such as cuts, abrasions, or exposed conductors. The connections should be checked for tightness and corrosion. Any damaged or deteriorated control cable should be repaired or replaced promptly to prevent further problems. In addition to the NEC requirements, there may be other applicable standards or regulations that govern the installation and operation of control systems. For example, the National Electrical Manufacturers Association (NEMA) publishes standards for various types of electrical equipment, including control cables. These standards may provide additional guidance on conductor size, insulation type, and other factors that can affect the performance and safety of control systems. It is important to be familiar with all applicable standards and regulations to ensure that the control system is installed and operated in compliance with all requirements. When selecting control cables, consider the environmental conditions in which they will be used. Control cables that are exposed to harsh environments such as extreme temperatures, moisture, or chemicals may require special insulation or shielding to protect them from damage. Control cables that are installed in hazardous locations, such as areas where flammable gases or vapors may be present, must be listed for use in those locations. Hazardous location control cables are designed to prevent the ignition of flammable substances in the event of a fault or malfunction. When selecting control cables, it is also important to consider the flexibility of the cable. Flexible control cables are easier to install and route than rigid control cables, especially in tight spaces. Flexible control cables are also less likely to be damaged by vibration or movement. Control cables are available in a variety of constructions, including stranded conductors, solid conductors, and shielded conductors. Stranded conductors are more flexible than solid conductors and are less likely to break or fatigue. Shielded conductors are used to protect the control signals from electrical noise and interference. The type of conductor and shielding required will depend on the specific application and the level of electrical noise in the environment. When installing control cables, it is important to use proper wiring methods. Control cables should be supported and secured to prevent them from sagging or becoming damaged. Control cables should be run in raceways or cable trays to protect them from physical damage. Control cables should be separated from power cables to prevent electrical noise and interference. When terminating control cables, it is important to use proper termination methods. Control cables should be terminated using appropriate connectors or terminals. The connections should be tight and secure to prevent loose connections or shorts. Control cables should be properly identified to facilitate troubleshooting and maintenance. Control cables can be identified using labels, tags, or color coding. The identification should be clear and durable to ensure that it remains legible over time. Regular testing of control cables is important to ensure their continued reliability. Control cables should be tested for continuity, insulation resistance, and voltage drop. The testing should be performed by a qualified electrician or technician. Any control cables that fail the testing should be repaired or replaced promptly. The NEC is a comprehensive set of standards and regulations that governs the safe installation and operation of electrical systems. It is important to be familiar with the NEC requirements when working with control cables and other electrical equipment. The NEC is updated every 3 years, so it is important to stay current with the latest edition. In addition to the NEC, there may be other applicable codes and standards that govern the installation and operation of control systems. These codes and standards may vary depending on the location and the type of application. It is important to be familiar with all applicable codes and standards to ensure that the control system is installed and operated in compliance with all requirements. When in doubt, consult with a qualified electrical engineer or contractor.